the way that you write the previous, the notation for that, a sub n minus 1, that means the previous term. So whenever we write a sub n minus 1, a sub n is the nth term, but a sub n minus 1 is going to be the notation for the previous term. Because if we want to find the second term, that means n is 2, a sub 2 minus 1, that's a sub 1, which is the previous. If we want to find the 10th term, 10 minus 1 is 9th. We have to use the 9th term in order to find the 10th term. We have to use the 10th in order to find the 11th, the 11th to find the 12th, and so forth. So that's why there's this initial condition. You are given the first term. After that, that first term is used to find the second, second to the third, and so forth. So some sequences, you can write both explicit and recursive, okay? Yesterday, when we did those first examples, and some of them were not arithmetic or geometric, but we could have written a recursive definition for that. There was still a pattern, it just wasn't add or subtract or multiply. Okay, so we could always write a recursive. So this particular sequence, we could write either one. So from yesterday, if we write explicit, okay, that's just from 14.1, we took a sub 1 plus n minus 1 times the common difference. 23 minus 3, 20 minus 3, 17 minus 3. So our common difference was negative 3. And remember, we distribute and combine like terms. So a sub n would be 26 minus 3n. That was from yesterday. That would be an example of an explicit. Just remind you of what we did yesterday. For recursive, there's going to be two equations, two parts. You have to state the initial condition, and then you state your recursion equation. So kind of what's happening. So our initial condition would be a sub 1 equals 23. Our recursion equation would be a sub n, and then we're always going to use the previous term, which is a sub n minus 1, and then what are we doing to the previous term to get to the next? So we look at this. What are we doing to 23 to get to 20? 20 to get to 17, 17 to get to 14. That's a pretty easy one. We are subtracting 3. So that is an example of a recursive equation. So today the examples, you're either going to be given the recursive equation definition and you find the certain terms, or you're given the sequence and you have to find the recursion equation. The most important part is it has to have initial condition. If we took away this initial condition, and I just gave you this, a sub n, you didn't have this or this, I just gave you that equation, and I said a sub n minus 1 minus 3, you would have no way to know where to start. You have to be given this initial condition for a recursive definition. Explicit you don't, but here you do. Okay, so these first examples are just find the third, fourth, and fifth term. It gives you the recursive definition, it gives you a sub 1, and it gives you the recursive equation. So we just use that to find the third, fourth, and fifth. But like yesterday, we can't start with the third. We're given the first. We have to find the second in order to find the third. Then we use the third for the fourth, and so forth. So a sub 1 is 5. We have to find a sub 2. We use this formula right here. The previous, remember this stands for previous term. The other thing you could do is, if you can't remember that, plug 2 in for n. If I plug 2 in for n, I'm going to do that real quick. You don't have to. 2 minus 1 plus 3. Well, that's equal to a sub 1 plus 3, which is the previous. A sub 1 is 5 plus 3, so we get 8. So our second term is 8. Now, you don't have to do that every time, especially maybe right now, that makes more sense. Or sometimes it gives you a bunch, like it gives you maybe a sub 1, 2, and 3, and then you have to find 5, 6, and 7. But here it just gave us the first one. So now for a sub 3, we could do that again. We could plug in 3 right here. 3 minus 1 is 2. We need to use a sub 2, or we can just know that's the previous. The previous term to the third term is the second term. So the previous is 8 plus 3 is 11. A sub 4. The previous to 4 is the third term. The third term was equal to 11 plus 3 is 14. And then we want the fifth term, so one more. A sub 5 equals the previous plus 3, 17. So there are your third, fourth, and fifth terms. Even though it didn't ask for the second, we had to find the second in order to find the third. And some of you can do that. I don't have to see 8 plus 3. Okay, if you can just tell me 11, 14, and 17, just be sure since there's 3 numbers, you assign what they are. Tell me which one is a sub 3, a sub 4, and a sub 5. All right, so a sub 2 is equal to 2 times the previous. The previous term to the second term is the first term, so it tells us that's 4 minus 1, so 8 minus 1, we get 7. That's not part of our answer, but we need to find the second in order to find the third. So now we can start finding our answers. So 2, I'm just getting this from the recursion equation, times the previous. The previous is 7 minus 1, 13. A sub 4, the fourth term is 2. The previous now is 13 minus 1. So 26 minus 1, 25. The fifth term, 2 times the previous. Now the previous is 25 minus 1. So we get 49. So there are your third, fourth, and fifth terms. Okay, because you're finding 3 again, don't just write 13, 25, and 49 somewhere. Okay, tell me which one is which somewhere so that I can see which one is which term. Whenever you're finding more than one, I need to be able to know which one is which. All right, this one's a little different because we have a sub n plus n. Just like before, we have to find the second before we find the third, fourth, and fifth. So a sub 2 equals, remember this is the previous. So the previous is 10 plus n. Okay, well n is the number of term you're trying to find. So in this case, a sub n is equal to 2. So for the second term, n is 2, and we get 12. For the third term, we take the previous. Now the previous is 12 plus n is no longer 2. Now n is equal to 3. For the third term, n is 3, so plus 3. For the fourth term, we take the previous, 15, plus n. Now n is 4. For the fifth term, we take the previous, 19, plus n. For the fifth term, n is equal to 5. You get 24. So there are your third, fourth, and fifth. So n is sometimes involved also, and we'll use that in a second when we write our own. When it's backwards, it gives you the sequence, and you have to write the recursive definition. All right, this one even a little bit different. It gives you the first and the second term, and it uses both of those in the recursion equation. So it gives us a sub 1 is 2. It gives us a sub 2 is 4. Okay, now I'm going to write this one. So a sub n, all right, 3, a sub 3. If this one seems a little tricky for you, you don't know which one is which, let's plug that number in. So a sub 3 equals a sub 3 minus 1 times a sub 3 minus 2. Again, I don't have to see this every time. I'm just doing this in case you're getting a little lost. So 3 minus 1 is a sub 2. 3 minus 2 is a sub 1. So it takes the previous times the previous to that. So the two previous numbers. So for the third, we take the previous times the previous to that. So a sub 2, it showed, was 4. A sub 1 was 2. So 8. So a sub 3 was equal to 8. A sub 4 is going to be the 2 previous to that. So it's going to be the previous to 4, which is 8, times the previous to 8, which was 4. So we get 32. And then a sub 5 is the previous to 5, which was the 4, and the previous to 4, which was 8. 32 times 8, 256. Excuse me. So if writing the numbers in every single time like that helps you, then you can do that. It's not necessary. I don't have to see that, but if you need to, if sequences and series blow your mind, then do that. Some of you really good number sense, and you can see that just like that. Like this is easy, easy, easy. If it's not easy, it's not going to be difficult for you. You just have to write more stuff down. If you can do it in your head, terrific. If you can't, be sure and write as much down as you need to. All right, so now these next ones give the recursive definition. Now, this table over here, nothing that I ever have to see. This is just for if you're having trouble seeing the pattern. This is one thing I've just kind of come up with that I think is helpful, that has helped people in the past. Not anything that you have to do. And maybe this table, on some of them you need it and some of them you don't. Okay, but if it's hard to see the pattern, like on this one when we look, 81, 27, 9, and 3. Most of us can probably see the pattern right there, that we are dividing by 3, divide by 3, divide by 3. So you're doing the same thing every time. So that's a pretty easy one. You probably don't have to think much out of. So recursive definition. We need the initial condition. Initial condition is just what does A1 equal? That is given. You just have to know to write it down. Then A sub n equals, we'll always use the previous. Okay, that's going to be part of your equation all the time as well. We've just got to figure out what to do with this previous. So what did we do to 81 to get to 27? What did we do to 27 to get to 9? 9 to get to 3. We divided by 3. Multiply by 1/3 out at the end, multiply by 1/3 at the beginning. Use the little divided by 3 sign. Any of those will work. Do the slash divided by 3. As long as you show me multiply by 1/3 or divide by 3, that is what I'd like to see. So again, there could be a 1/3 out in front of the A sub 1. There could be times 1/3 on the end. Divide by 3 using the slash, the line with the 2 dots, however you want to show that. Pretty easy one also. Initial condition is always easy. Hey, everyone should get that right every single time. Don't forget to write it, though. You have to have it for a recursive definition. Not explicit. Explicit is just an equation, but recursive you have to. So then we have A sub n. And what are we doing to 9 to get to 13? 13 to get to 17. 17 to get to 21. Again, a pretty easy one. Most of us probably don't have to think very hard on that. We're adding 4. And so there's your recursive definition. Again, pretty easy one. All right, this one, maybe looking at it right away doesn't seem that easy, but remember, we have A sub 1 equals 1, A sub n equals A sub n minus 1. So I'm going to do this one on this chart. This one's not difficult. Some of you probably already know the answer to all these, okay? So what I think this chart helps us, A sub 2, so the second term, we're going to take the first term and do something to it to get negative 1/2. And then we're going to take negative 1/2 and do something to that to get positive 1/4. Then we're going to take 1/4 and do something to get negative 1/8. So again, if you don't see patterns very easily, then this chart might be something that helps you. Nothing that I would ever have to see, just something that might help you get the pattern down. Because whatever you're doing has to be the same for each of them. So just kind of start by picking something that would work. So the first thing I think of is multiply by negative 1/2. And then I just see, does that work all the way down? If I multiply by negative 1/2 all the way down, does that work? And it does. This is negative 1/2. Then we have a negative times a negative, gives me a positive. Negative times positive gives me a negative. Notice that multiplying by negative 1/2 worked all the way down. So just like the divide by 3, you can divide by negative 2, put the negative 1/2 in front, at the end, whatever you want to do. Since I already wrote it right here, I'm just going to do times negative 1/2. Now, do not a sub n equals a sub n minus 1. If you do that, that means minus 1/2. Okay? Don't just write it next to it. If you write it next to it out in front, negative 1/2 a sub n minus 1, that is okay. That means multiply. This means subtract. So if you don't put parentheses or a little dot in between it, it means subtract. Whatever you meant it to be, you write what you mean. Okay, so again, if you use parentheses, then it's not a problem. Divide by negative 2 would be fine as well. All right, so here we have a sub 1 equals 1. A sub n, we're doing something to the previous to get to the next. So when we look at that, if I add 2, I get 3. If I add 2, I get 5. So adding didn't work. Multiply by 3 didn't work. Dividing isn't going to work. So this one's going to require a little bit more. So this is where some of you can see this pattern right away. You already know what it is. But if you don't, then this little table might be helpful. So we're going to take the previous, do something to it to get 3. The previous, what are we going to do to get 7? What are we going to do to 7 to get 13? 13 to get to 21. 21 to get to 31. Now this is going to require a mixture of things. Okay, it's not just flat out one little thing. So what I do on these is I start out just like adding and subtracting or multiplying. Okay, what is a simple thing to do? So here, if I add 2, that gets me 3. If I add 4, add 6, add 8, and add 10. Now, obviously, adding 2, 4, 6, and 8, we can't show that in a single rule. So we've got to do some more splitting up. So the next thing to do, since all of these are even numbers, what I would do next is say plus 2 times 1, plus 2 times 2, plus 2 times 3, 2 times 4, 2 times 5. So I'm getting closer. I've gotten one thing that's the same. So now I've got 2, 2, 2, 2, and 2. Okay, so I'm done with that. I'm not using that anymore. But I still got to figure out 1, 2, 3, 4, 5. That's different all the way down. So I've got to figure out how to get a 1, how to get a 2, 3, 4, and 5 using the same rule all the way down. So this is where the n comes in. Remember back here, this problem, this was 2, 3, 4, 5. So it changed every time because we could use the letter n. So if we use n, that's something that changes every time, but we can write the rule that makes it the same. All right, so here n is 2, but we need a 1. N is 3, but we need a 2. N is 4, we need a 3. 5, we need a 4. 6, we need a 5. Well, there's a way we can figure out it's 1 away from what we need. So since it's 1 away from what we need, we still have the plus 2. And the way we can use the n, we can say 2 minus 1. Well, n is equal to 2. Here we can say plus 2. We need a 2. N is 3, so n minus 1. 3 minus 1 gives us the 2. The 2 is the same. I need a 3, so n minus 1. 2 times n minus 1. See how that works all the way down. So that's something else that you could, it might have just been 2n. So if this was 2 times 2, 2 times 3, 2 times 4, 2 times 5, it might have just been plus 2n. It just depends what you need. Use the n whenever you get whatever's happening to be one thing, okay, one digit away, we needed a 1, there was a 2, anytime it's 1 away, then that's when you know you're going to use your n. So our recursion equation over here is going to be plus 2 times n minus 1. And that's a pretty difficult one for most people, okay, seeing that pattern. Again, if you're good at number sense and seeing those patterns, you might have had that a long time ago. But if not, use that little table if it's helpful. Okay, if it's not helpful, don't use it. I would never have to see this. This is just something, a tool that I found to be useful for some people who can't see the pattern that well. All right, and then this last one. So again, we can always know a sub 1 equals a sub n equals a sub n minus 1. We know at least that much. We just got to figure out, what are we doing to 1 to get 2? 2 to get a 6. 6 to get a 24. 24 to get a 120. And 120 to get a 720. If you already know, terrific. If you don't, here, I could add 1 and add 4, add 18, but that doesn't really give me any kind of pattern. So if I multiply by 2, multiply by 3, multiply by 4, times 5 times 6, notice those are 1 away. And a lot of times if you don't see the pattern, when you see it on paper, now it comes to you. So if you make this table and you see 2, 3, 4, 5, 6, and we say a sub 2, n is 2, n is 3, n is 4, n is 5, n is 6, we can replace this with n. So all we're doing is we're taking the previous term and multiplying it by n. And there's your recursive definition.